Welcome. In this lecture, we are going to talk about step by step guideline for digital control implementation using FPGA. So, here we will first talk about our hardware setup prototype, then digital current mode control buck converter with closed current loop, a short video will be presented, and the summary of step for FPGA based implementation. So, the digital control current mode control implementation uses FPGA in a buck converter. So, here if you recall lecture number 15 where we have talked about mixed signal current mode control, and in this case we are talking here a DC-DC converter and this is particularly we are using a buck converter. So, this any DC-DC converter can be used and we are using current, inductor current, and then this inductor current, we are using a sensor, definitely there will be a sensing gain and this will convert into a some sense voltage. We can sense the output voltage by through an A to D converter, but since initially we are using a fixed current difference. So, that is the peak voltage which is going out of the digital loop and it passed through a D to A converter and this is generating a peak current voltage reference. That means, we are talking about this peak voltage, equivalent voltage, and this will be compared with a sense voltage. That means, this is our V sense which is analogous to our inductor current. That means, this is a sense voltage corresponds to the inductor current. So, this is what is expected from these two signal here I am showing here. So, here we are using a fixed current difference, that means Vp is fixed, this is fixed. That means, this is the inner current loop closed, but the outer voltage loop still open, because we just want to show some implementation demonstration in the subsequent lecture in this week. So, here mixed signal current mode control with closed loop. Next, this is a setup and we have discussed that this setup can be arranged for buck mode as well as the boost mode. So, this actually are not now we are using like a buck converter, and this is our signal conditioning board and in the bottom of this will be FPGA. So, now we are going to implement mixed signal current mode control. So, we have discussed that we are initially using fixed current difference, that means Vp, and that is compared with our sense inductor current like this. So, this is our sense VSN, sense inductor current, and in this case this DC-DC converter which is here is in this board and it has the current sensor and everything in this board, voltage sensor, then up, and also we are providing gate signal from this particular board. Okay, so the gate signal and the gate drive is also in the PCB. Next, we are talking about ADC, DAC, these all are in this board, these all are in this signal conditioning board, and then this digital platform where we are implementing this logic is in the FPGA. Okay, so that means we are using the digital control algorithm. So, this platform only deals with digital signal, only digital signal, only digital signals. That means, output of the ADC it will go to the FPGA, then from the FPGA will generate the digital value which will go to the DAC, that means D to A converter, and the D to A converter is sitting in this mixed signal board. So, we are using FPGA as the digital control platform and we are using a Xilinx FPGA. So, now we are going to see a short video where we will show the full implementation, that means the live the implementation of the mixed signal current mode control with inner current loop closed. So, now we have just say we have seen the live demonstration of the mixed signal current mode control, and you can see in the we are using an oscilloscope to actually display the inductor current waveform here, and we are using a current probe. This is the current probe we are using. Okay. So, we are using a current probe to display the inductor current, and this current probe result is shown here. This is a current probe result. Now, so this is our current probe result, inductor current, and we are also displaying the output voltage. This is the output voltage. So, this is my V out, and this is my actual inductor current, because we are using a current probe. So, this is my actual inductor current IL. Okay. So, you can see the periodic waveform, and here the current reference is fixed. So, we call it as a V peak or the peak current, since we are talking about the current here directly. So, it is better to use in this case as if like an I peak in the analogous sense. It is like there should be an I peak which will limit the current. Okay. And this is a power supply, and this is our actual kit, which consists of this power stage board, signal conditioning board, and at the bottom there will be an FPGA, the complete setup. Here we are using a fixed current reference, and the inductor current is just touching this, but in the subsequent lecture we will do closed loop. So, in order to implement, what is missing here is the computer, because we need a computer to actually generate the code bin file, and that bin file will be, so computer will generate the .bin file, and this will be loaded to actual FPGA, and this FPGA kit is here. So, then once you dump it, then computer is nowhere in the picture. So, the real controller implementation or the real time FPGA actually control the whole DC-DC converter. So, in order to go to that computer, how to generate that file, bin file, so that you can dump into FPGA. So, first we have to identify the control logic. That means whether you are here, we are talking about the peak current mode control with constant current reference. Though we are not going to present the whole code, because we have not yet started the Verilog programming, and that we will be discussing in the subsequent lecture. Second thing, we have to synthesize that code, the first step. Third step, we have to generate the bin file, and we have to load into the FPGA, that we have discussed here. Okay. So, here we will be discussing in detail about this Verilog coding when you go to the actual FPGA class, that will be coming in the next week. So, in the FPGA we have to install the Xilinx ISC. Again, this is just for Xilinx, I would say ISC. And it is not mandatory for I would say to implement this or to install this software, but at least you should have some visual understanding how do you implement the digital control. So, we have to create a project, we will discuss about this. Then under this project you have to write a .v file, that means you have to write a Verilog code, and we will discuss in detail Verilog HDL. We can also use VHDL, but I am just talking about Verilog HDL. So, that means your code, whatever you want to implement, should come, and I am not showing the code because unless we actually discuss the code, it may not be a good idea, but I am just saying that whenever you go to the next week Verilog code, we will first show that how to create a project, then how to write a Verilog code, add it. In addition to that, that means we need to add a new source file into the project, and here since we are going to implement it, we have to use a implementation constant file, because in FPGA there are lot of digital pin, because lot of digital pin. So, each pin has its own address, that means every pin should have its own address, otherwise it will not be unique, you cannot identify. So, with this UCF file, user constant file, that is the implementation file, the job of this file is to indicate, because whenever a vendor, maybe like a Xilinx commercialize this FPGA or any other third party make the kit, they make sure that, because Xilinx FPGA, if you go to the FPGA kit that we are showing here, we are talking about this FPGA is made by Xilinx, but this whole kit is made by Nomato Lab in association with Xilinx. So, you need to know the address of this pin, not the FPGA pin, because this pins, what is the address that you have to define. But eventually some of this pin will be connected to the FPGA pin. So, naturally this address of this pin will ultimately get reflected into the address of this pin, but it depends on how they are connected, what the routing is used, like whether this pin is connected to this pin or not, that will be given. So, that means you need the UCF file to clearly highlight that what are the pin configuration, what is their address, and when you go to the actual implementation, we will show it. Once you create the UCF file properly, that means you want to send the gate signal through the gate signal, and you want to generate that gate signal, and you want it to be available, let us say this pin number 1. So, the pin number 1 will be some address. So, you have to make signal out, that means through FPGA you have to make signal out. So, that means you have to give an out pin and this gate signal go to that particular pin. So, we will discuss about this, but today we are just discussing the steps. So, there is a UCF file, then assuming that you have already written a Verilog code and you also have an implementation file. Now, you are ready to import your code, run it, synthesize, generate the bin file and load it to the FPGA. So, it is again not complete. So, you have to write a Verilog module for the control implementation that you are going to do. Once you test it fine, then once you have ready, then you have to go for rerun all, that means the synthesis step. So, this is the step synthesis, and this step will generate all the RTL, everything, that means we will discuss about RTL and how to synthesize in the next week in detail. Then once your synthesis is done, so till synthesis you do not need to bother about user constant file, because you are not going to implement. You can even check simulation whether my algorithm is working fine, whether are you getting the right algorithm that let us say I want to implement an AND gate or OR gate or any other full adder, 4-bit adder. So, you have to check that. Once you are satisfied, synthesis is complete, then you go to the next stage, which is the implementation stage, and this stage required that you have properly defined the user constant file, UCF file. Once you rerun, then it will generate the program file. That means in that module you are generating the programming file, and this programming file means whatever synthesis you made, if you want to implement with actual FPGA, which pin, which blocks it will be occupied, where it is going to dump. So, all this routing and all information will be available in this program file, where you are going to go for, in the last step we saw the implementation of the design. So, this comes under a separate then generate program file, that means we have successfully implemented. So, implemented means it will translate your design synthesis, how it will be routed to lookup table, because we will discuss. In fact, if you recall that in the very first week we have discussed about something regarding FPGA, that is the lookup table, and then we have discussed that configurable logic blocks. So, where we have understood that if you want to implement one particular gate in FPGA, then how can you do using lookup table and configurable block. So, this will be translating into those configurable block, then it will map, because there will be thousands of such blocks will be available. So, which block should be taken, and we have also discussed the field programmable gate array, not only configurable block, there will be multiple configurable block, how they are interconnected, then what are the IO pins will be taken. So, all these will be mapped. Then you have to route, place and route. How do you connect? Because you have to consider the actual input output pin as well as the internal routing. So then once it is complete, then your implementation is over. Now you have to generate the program file. So once you generate the program file, so that means if you zoom this part, generate the program file, implement, you have to see the process property. That means in the process property, you have to go general option, where you have to choose the bin file. That means here you can see run design rule checker, create bit file and binary file also. So these two are the default one. So you have to also select the bin file, and then you have to also enable this CRC check, and this is your UCF file linking. So that means your implementation is done, you have generated the bin file. So this bin file is the file which will be dumped into FPGA, and it will create automatically all this routing. And in this software in the computer, it has a library which has a similar library of the actual FPGA, because every FPGA Xilinx, we are talking about Spartan 6. Okay. So under Spartan 6 there are n number of, now many variants are there. So which variant, what is the part number of the IC? IC part number. So everything is important when you generate this program, because we will discuss, otherwise it will give totally wrong result. So you have to specify all this, then it will generate the bin file, and once the bin file is generated, we have discussed. So once you generate the programming file, then you run it, then it will generate the bin file. So you have to select the bin file, which is the bin file. That means the program name is main module. So we have a main module .v file, then it will generate correspondingly main module .bin file after this stage, and you have to search this main module .bin file. Then once you search it, then you also have to check the ports, because you have to, this will go to, because you have to connect an USB cable from your computer to that USB-C type cable, which will go to your FPGA. Okay, FPGA also have a USB port. So then before you send this out, you have to make sure that your port address is defined properly. So that means you go to your device manager in your computer, check the port, check the existing connected port. Once FPGA is connected, that means if you connect your FPGA, then new port will be visible. That means your new port USB serial. So it is a COM5, that means that is the port is COM5. So that means your port is selected. Now you have to select, you have to give another software, is a MIMAS software, MIMAS, you can see. So this is a app. This app will actually interface between your computer and the FPGA kit, Nomato FPGA kit. In the MIMAS software, since you have connected FPGA in the common COM port 5, which you have checked through device manager, you have to select in the MIMAS software that I have selected COM5 from the select port. So this must be consistent. Once it is done, then you have to do open file. That means you have to dump this code into FPGA. So you click the open file here, you select the port correspondingly, then click on the open file. Then in the open file, it will ask for the directory where you kept your main module.bin. Select that and select this particular file. Once you select, that means the selected file selector will be written like this. You have to make sure that you have selected the right bin file, then you program. Once you program, the program will actually have this green line to show the progress. It is done, it will show that programming done, and it is rebooting FPGA. So then FPGA, it is dumped into FPGA. That means if you go to the FPGA, if you go back, I will show you that this particular key. So, once you dump, then there will be a LED light. So, before you dump, the LED light will glow. Once you dump, it will turn off. That means your FPGA is ready. Now you can start the operation. That means we have discussed that your program is dumped into FPGA, bin file is selected, COM port is selected, and then main module is selected. Then you have program it, and program is successfully installed, and then it will actually your FPGA run. So, whatever you have shown the video clip, actually it is after this programming. Now FPGA is ready. It will generate the digital output, and then DAC will convert it to analog voltage. It will compare with the sense inductor current, and by that way it will implement the current mode control with only inner loop close. So, in summary, we have discussed hardware setup prototype, we have discussed digital current mode control buck converter with closed current loop, and we have also demonstrated a short video, and we have summarized the steps for FPGA implementation. So, in the subsequent lecture in this week, we will show the actual hardware case studies, where we want to show actual current mode control and how to use mixed signal oscilloscope to check the validate your operation, closed loop operation of the DC-DC converter. Then if there is any stability issue or instability issue, what is their power spectrum and how does it look like. So, all these things we will be discussing in the remaining lecture in this week. That is it for today. Thank you very much.